Thank you, Peter and folks, for helping me check. Good. Okay. Good. So let's write them out. A lot of people did well on this, but I'll just do it with you here. Just again, make sure everyone who is still kind of struggling has some thoughts about how to do it. Again, we're going to use like a limit as n goes to infinity. The letters aren't that important, I guess, but we'll stick with the letters we used yesterday. K will be the index of the sum, and we had that running from like 1 to n. Usually, that's an agreement. Some of you came up with some other creative ways to do that, but like I think that's how we might like to do it, just for fun, you know. Good. And then what are we adding up? We need to add up like n rectangles, and the size of those rectangles is going to be, in general, b minus a over n, right? So in this case, that's nice. It's just 5 over n. So that's the change in x, and then now we need to like figure out how to plug stuff into this function in like a systematic way. Now if we're doing, I think most of you are doing RRAM, right? So if you're using RRAM, then and you want the very first increment away from 0, then that's just given by your delta x. For this case, 0 plus delta x gives you the right-hand endpoint of the first interval. So that's what we want to plug in. And then how do you get the right-hand endpoint of the second interval? Well, I think we need 2 times delta x. And in general, if you want the kth subinterval right-hand endpoint, it'll just be k times delta x. So that's exactly what we'll put in here. In this case, it's 5 over n times k, right? So 5 over k. 5 over n times k, right? So that gives you, I mean, verify that actually makes sense. As you plug in, just like yesterday, if we plug in 1, does that give you what you want? If you plug in k equals 1, you get 5n here. That's us plugging in 1 delta x into our formula. Does that give us the right endpoint of the first subinterval? I think it does. And if you plug in n for k, does that put us at the very end? It should just put us at f of 5. Right? And if you put n in here, that is what we have here. We just are plugging in 5, aren't we? So that just do a little bit of kind of reality check on these two, make sure they actually seem right. That looks good. Yeah. All right, let's do this one. And then I do have one more comment to make about this and about some of those last interesting kind of challenge questions that were on the thing from class. So this is an interesting question to kind of run this backwards. This is some definite integral. You got to reverse your thinking. Now, if conveniently, we haven't like multiplied anything out. You know, it's obviously this could be other things, but just from the form of this, we can make a guess that I think this is our delta x here. If that's our delta x, then our interval is still of size 5. In fact, this does look kind of similar to what we just did, doesn't it? Looks like our function is 3x to the 4th plus 1. But it's not 0 to 5. How can you tell that it's something else? I mean, I know some of you got it out there, but
It starts at 2.
yeah, it looks like if you start plugging in 1 for k, 2 for k, what are you getting? Well, you're getting 2 plus delta x, and then 2 plus 2 delta x, and etc. It looks like we're starting at 2. And if you plug in n, again, the very last thing you're going to plug in is k equals n. And if you plug that in, you get 7. So it looks like we're starting at 2 and ending at 7. Again, we already know that the size of that interval, b minus a at least, is 5. So I think that would be a good answer for that second one. So one thing I want to say too about this is that I hope you understand that we've taken this to the place where we can actually evaluate these without thinking about integrals anymore. If you can write one of these this way, we've turned an integral into a new problem, and that's evaluating this limit. If you can find a formula for this, like that gives the sum of the first n terms of this series, then you can maybe take that formula and take the limit as n goes to infinity to get your answer. So that's the flavor of the last problem. I thought I'd just show you the answer to that last one too. We can work it out here. Is it just it's x cubed, right? The one from the homework, x cubed from something to something. This is exciting because we actually get to evaluate the limit exactly. We actually get to find out the exact area under the curve from 0 to 5, right? So we'll do the initial setup. This is not the exciting part, but it's good review. A goes from 1 to n of, we got an interval size 5 again. I don't know why that's our favorite right now. 5 over n times x cubed. So that's going to be what? 5 over n times k, right? So I think does that sound good? And by the way, this is this is number 12, too, right? And then number 15 on that worksheet. So this will be giving you 2 answers on this, on the back there if you hadn't done them. So what does that all come out to? Yeah, 625 k cubed over n to the 4th, if you work all that out, right? Which is one of the multiple choice answers. I don't know which one, but yeah. Cool. But now, one other thing we said you can do in pre-calculus, and then I think I reminded you on one of these activities here, is anything that doesn't involve a k inside this argument of the sum can be factored out. So we can actually do this. The 625 and n to the 4th can be factored out. And really the problem we're left with is, can we sum the first n cubed numbers, right? Is there a rule we can establish for that? And with ingenuity, you could maybe figure it out, or this is not the focus of this class, so I just gave it to you. Right? It's what? What does it say there? I mean, these are not obvious necessarily, but the sum of the first n cubed numbers does have a nice closed form. This is not always true that this is available, but what does it say? This is not something I had memorized. N squared times n plus 1 squared over 4. Do you understand how I can do that replacement? Apparently, and you can try this. Let's just try it real quick. Is this really the sum of the first n cubed? Like, if you plug in 1, do you get 1? If you plug in 1, do you get 1? If you plug in 2, do you get 9? If you plug in 2, if you plug in 2, 2 squared is 4. 3 squared. Does it work? Okay, is 9 good? And just if you're in disbelief that we have such a formula, try one more and see that we get what's 27 and 9 is 36. Try plugging in 3. Do you get 36? Does this seem to be summing the first n cubes? I think this formula does work. I mean, you can just take our word for it too, but I don't know. It's pretty startling that we have such a formula. But again, not part of this class, but it would be interesting to. Well, we did prove some things like that. We took pre-calculus last year and the induction proofs. You did prove some things by induction, but still, how do you obtain these results is an entirely different question. Like, where did they even come up with that result is another question. And I'd love to discuss that with you sometime if you want to come by, but it's not part of this class. Anyway, this is cool. Are we good? Now, it should be fairly clear from our limits. If that's true, then we can just take the limit of this. This is n to the 4th up here too. This is an n to the 4th. So do you see that we'll get 625 over 4, right? Okay, good. Which is great because, again, just take a look at what we did. You're like, okay, I see that. That makes sense. That makes sense. But just take a look at what we were started with. This is an integral, a definite integral. This is the area under like a smooth curve. And you just calculated the exact value of the area under that curve, right? So I just want to make sure you understand what's at the beginning and at the end of this equality. Right? That's pretty cool. Feel free to like num int this and see that you get 625 over 4, you know? Anyway. So that's part of the reason this is exciting. We won't be making you go, you know, this is the place where we are fine stopping, but I thought it is fun to just see that you can actually, if you can try it, if you can resolve that, then you can get the actual area under the smooth curve. Anyway, good. Enough about that for now. You can check your answers against the answer keys when they're posted online. Make sure you're feeling good about all the ins and outs there. By the way, this is the maiden voyage of that lesson. This is a new thing AP has added, the limit definition of the integral. So this is new for us teaching that. Hopefully you benefited from it. They just started putting questions like that on AP.
is gonna be the definition is gonna be
Yeah, a good reminder, we have a quiz tomorrow. It has everything on it, including up to what we just did yesterday. But it does not have things about average value, which is what we're going to talk about right now. All right, so we're going to talk about averages today. That sounds like a pretty easy idea, but we'll of course try to make it as complicated as possible. Okay. So if you wanted to average 5 temperatures, for example, I think you would know how you would do that. You would sum them. You can already see we're going to talk about sums here, of course. We're going to sum them up and divide by the number of temperatures that you have. For these, you'd add them up and divide by 5, but in general, you would sum all the temperatures and divide by n if that's the number of temperatures you have. So what if, here's the question that really motivates today. What if you had some smooth function that gave the temperature over time throughout the day, and you wanted to ask the very innocent, simple question, what was the average temperature? Obviously, this is not a set of discrete temperatures throughout the day. It's a function, it's a continuous function, and yet we still have every right to ask what is the average temperature throughout the day. So that's the question that motivates today. But I think we can use the same kind of thing we just did here. As always, let's pretend that it looks like this. That I know how to sum. That I know how to sum. And we can even think about some of the things we've just been talking about, right? B minus A over n, that gives our delta x. That also means that if you solve that in this particular case, that n is equal to 24 over delta x if you choose delta x to be a particular thing. We'll need that in a second. So I'm going to return to this formula I just had up here a second ago. Except instead of like discrete temperatures, I've got these function values, say, that come from this green f of x curve. Now, I think we just said that n is 24 over delta x. So if I actually write that sum out, I get f of x1 plus f of x2, n of those up top. And on the bottom, I get 24 over delta x. So in general, I know this is a crazy way to do an average, but this would do it for us, right? If we had a set of discrete values. Here are all those values. Here's delta x over 24. Or, using summation notation, we have this. I just decided to pull the delta x in, right? I'll give you a second to digest. Think about it. You should predict my next move, obviously. That's not where I'm going to end. I'm going to do one more thing there. I'd like to get the exact value of the average, not an approximation, right? Take the limit, I hear you say. Is that good? Sorry. Wait a while. No while waiting. Okay. We'll move on. All right. So that's the expression we had in the last slide. Except I've asked, as usual, let's take the limit as n goes to infinity. So that's the only difference. Notice I've changed this from an approximation to an equal sign. And this gives 1 over 24 times the limit as n goes to infinity of that, which is, of course, the definition of the integral of a function, right? So that's not a huge surprise, maybe even right away when we first even mentioned the word average and we thought, hey, we're going to have to sum something up, you already maybe were thinking that this was the direction we might go. I don't know, but there it is, sure. So in general, how do we find the average value of a function just in general over some interval a to b? How does that work then, if we want to generalize that? Yeah, Rebecca.
So you take the integral and then you divide it by the number of or subsections.
Yeah, no, actually, I don't, do I actually have 24 here? 1, 2, 3, 4, 5, 6, 7, 8, 9.
So you divide it by the domain.
Yeah. Yeah, in general, we'll divide by the length of the interval, right? Yeah. In this particular case, before we write that up on the board here, what do the units come out to? What is this? What units does this have? This is, by the way, this is time in hours. This is temperature in degrees Fahrenheit, apparently. So what does the integral have for its units? Degree hours. So what do the units come out to for this? What is 24 measured in? Yeah, that's hours. So in the end, we actually do get degrees, which, of course, makes sense because we were looking for the average temperature throughout the day, and it would make sense that we recover the units of degrees after all is said and done. So just a little unit analysis on that as well. Degree hours are interesting units, by the way. I think that's an interesting unit. Degree hours, yeah. It's a degree hour. I don't know if I can lay any meaning on top of that, but there are lots of other units that we multiply by hours that make, you know what man hours are? That makes, you know what man hours are? Huh? Huh?
It's a man hour.
You know what a man hour is?
A man hour is working many hours.
So, yeah, I mean, I'm trying to think if I can do this with degree hours, but if I put if I put an hour into a certain job, we're all collaborating on I don't know, doing a new math mural on the hallway or something. I put an hour into it, Zachary put 2 hours into it. We're up to 3 man hours, right? Total, right? I don't know if we can do that for degree hours or not. I'm not trying to think. Yeah.
What if you guys both do it at the same time?
It'd still be 3 man. Let's return to an example that you know and love, and that's average velocity, right? Average temperature is fun too, but let's think about average velocity. Let me start by giving you some pictures of velocity curves. And I'd like to ask, what is the average velocity on these intervals? We'll start with an easy one. If you're going, make sure we interpret this exactly right. We're going 10, let's say meters per second. Meters per second for 2 seconds. That's your velocity is 10 meters per second the whole time. So what is your average velocity? Go ahead, Albert. You seem excited about this.
Oh my god, this is so
20 meters is how far you went. That's true. So what's your average velocity?
I'm sorry, is it 10? Is it 10?
Yeah, but velocity should be measured in meters per second.
Yeah,
or something.
20 meters per second.
So you did 20 meters, right? Because you did 10 meters per second, and you did it in 2 seconds. You went 20 meters, but you did it in 2 seconds. So that's 10 meters per second will be your average velocity. Which, before you even thought about it, if you're going 10 meters per second, maybe we don't always, the whole time, maybe we don't have to have the discussion. Your average is probably the speed you're going the whole time. Yeah, that's right, 10 meters per second though. All right, what about this guy? This time our velocity goes from 0 to 20 meters per second. 0, so you start at a standstill, but then by the time you're done after those 2 seconds, only 2 seconds, you're going 20 meters per second. So you're ramping up your speed. Yeah, don't think too hard. Don't second guess yourself too much. It is interesting to think about that. From an intuitive standpoint, do it. See if you can do it from an analytical standpoint. Josh, listen, guys.
It's still 10 meters per second.
Explain though.
In 2 seconds, it still has gone 20 meters.
Yeah, you went 20 meters.
In 2 seconds.
Now that we understand definite integrals, we understand why, like, the area under the curve might tell us that he's gone 20 meters. And he's still done it in 2 seconds. So the average velocity is 10 meters per second. I have that calculation up here too. The other way to think about it, though, is that, like, just intuitively, I think if you ask someone who never studied calculus, they might be like, well, if you started at 0 meters per second and you ended at 20 meters per second 2 seconds later, and you were doing that, you know, like, maybe the average is 10 meters per second, which turns out to be right too. There are a couple ways to think about it, maybe. Here's a curve, a velocity curve, under which I promise the area is 20 meters. So what do you think the average velocity is then? Yeah.
Well, I mean, that's 10 because if you already established that the average is the integral divided by the length of
Yeah, yeah.
the length of the domain.
Yeah, in fact, I like thinking about this picture here. Whenever, again, just like when we talked about earlier this semester too, it's almost like we assume afterward, if someone said, oh, I had an average velocity over those 2 seconds of 10 meters per second, it's almost as if you are pretending that they did this graph. Regardless of what they actually did, you're like, I don't know, maybe you did 10 meters per second the whole time, which is clearly not the case in these 2 pictures. But it's kind of like you're making that assumption. And I put those on top of each other because I like this kind of picture here. Can you imagine this being Play-Doh or something? And what would you, or up here, right? You don't have to imagine Play-Doh. You could take this piece of paper and you could like make a cut across here, couldn't you? And then like rotate that down. Because the key here is we have the same size interval, 2 seconds. And the claim is that for all of these, that the area is the same. I mean, it has to be if the average value, if the average rate of change is going to be the same. So I would claim the same thing must be true here. You must be able to like take slices of this and like shove it down in there, right? And have it fill in the same area. Because the area of all these pictures should be the same. Or because I told you they were, I guess. So you could like take Play-Doh and kind of smush it. If that was the graph, you should be able to like smush it down and have it be a rectangle of height 10. Yeah.
Is this to say, like, if we took all of them and smushed them downwards by the average, the integral would be 0? Like the same with your above and below?
Yeah.
here?
Yeah. So I think we're finally ready to say what Rebecca said in a box here. There it is. No, it's not in a box. That's a little disappointing. You want a box? All right, I got you. I got you. So informally, we can just think integral divided by interval, right? Which does have still like a semblance of a relationship back to like our elementary school notion of averages, doesn't it? Still like the sum divided by the total, kind of. Right? And we've laid I think the theoretical groundwork on the first slide there, why that makes sense and why that works. So when you're ready to do this, of course at this point we still need maybe the help of a calculator. So go ahead and set this up, show me this kind of setup, but then feel free to use your calculator to evaluate and find the average value of this parabola on this interval. When you're ready. Yeah, you will need a calculator. So did you get 4.5 up on top? So is that 9/6? I guess that's 3/2. Is that right? Yeah. Does that seem reasonable for that function? I mean, you could draw a picture. Oh, good. I have a picture prepared for you. Look at that. There's 1.5. Does that seem like the area underneath the blue curve from 0 to 3 just smushed all down into a rectangle? Right. It does seem like maybe you could take this area up here and like fill it in right there, right? We do have one theorem which I don't feel like comes up a lot in this course, but this is the time to say it, so we'll just throw it up here. It really is. In trying to think if there's really any difference between this and the regularity value theorem in some sense, but well, maybe you don't see yet why that would be true, but it is certainly true that if you at some point there's got to be a value of the function that takes on the average value. Or said another way, like that like smushed rectangle, the rectangle that we drew, that horizontal line should cross the function somewhere, right, that we drew. Which seems to have been true for all the pictures we've drawn so far. But we're just now saying that that's universally true. There will always be at least one point where that happens. So you can actually see that there might be 2 places on this curve where that happens here for this particular drawing that's down here. So this is that point, C, or this is, like I said, we'll call them C1 and C2. There are actually 2 places here in between A and B. Yeah, dude. Yeah, so again, continuity is required here for this. Yeah, you were saying like if someone uses this notation, then that's implied. It's actually not implied because there are other things that are integrable that are not continuous. Like, you can imagine if we have like a piecewise constant graph like this, like even though there's a jump discontinuity in it, you can integrate under it, right? So we actually do have to say like a working zero. So again, I honestly don't think that's used very much, but it's it's in the book. I don't know where else it comes up in this course really. We don't. Okay, I have 2 examples for you. Are you ready? Here we go. More average velocity, more motion. I like motion. This is good. Try and steal as much of the joy from your physics class as possible. Do it in here. Do you understand the situation here? We got a particle moving forward and backward in the line. I feel like we've done problems of this type earlier. And this is governing its velocity at any given time t. You plug that in. So, first task is, again, assign this task to your calculator if you like. I'm very interested in the second. I'm actually maybe more interested in the second question, and I'm interested in how you approach it too. The second question. Keep very careful attention to what the second question says. It's giving you different information. It's not just another same example.
We got 7.
Yeah, can someone just, I have my calculator here, but can someone just tell me what's the integral from 0 to 3 of v of t? The integral is what? 23.625, and then you divided that by 3? Or did you already do that? Is this an exact value?
Yeah, that's right.
And 7.875 is an exact value then. 7.875. Did I say that right? And the units are, let's give that to. Is that okay? Everyone okay with your FNN button on your calculator? It's working fine, right? Right, so that actually is very similar to the previous example. I don't have much more to say about that one. This is interesting to me though because again, the thing I'm giving you here is different. Why is this problem different? I'm giving you...
It's imposition, but we need velocity. So we
Yeah.
need derivative.
Yeah, maybe you could take the derivative. Go ahead, yeah. That'd be a good way to do it. It's wait, what? No, because you guys gotta get off your phone. The thing that's about to happen is gonna blow your mind. You just don't. You want to be fully present for what's about to happen. All right. So what did you find when you took the derivative? I put these on the same slide for a reason, right? What's the answer to this question? All right. So it is the same. Did you find that the derivative is the same? It is this velocity function here, right? Okay. So neat. So one way. This is the part that's about to blow your mind. One way to do this problem is to take the derivative and proceed as follows, right? And you get this answer. Yay. But let me remind you of something. You, along with like an Algebra 1 student, knew how to do this problem before today. Read it again and think about how you would have approached that if you were like had never taken calculus for a second. How would you have done it?
You plug in 0, 1, 2, 3.
No. What would you do? You plug in 0 and 3, right, into this function. So another, just verify that this works too, that x of 3 minus x of 0 divided by 3 minus 0 gives you the same answer, shouldn't it? Right? It's just change in position over time. Isn't that what average velocity also is? We've discussed it in the past, isn't it? So I think what we're about, does that mean we can calculate it in two different ways?
Yeah.
Does that mean we can do it this way, the way we've been doing it here? The average velocity is given by this. Or if we happen to have access to the position function, does that mean we can calculate it this way too? It seems to be that both are true. And it also seems to be that this 1 minus b over 1 over b minus a is somewhat negligible. It seems like maybe that's true, but I don't want to say too much because we've already gone too far. We've gone too far. I mean, what meaning could this possibly have? I mean, there's a derivative up in there, isn't there? All right, we'll unpack that later. But I just want to let that whet your appetite. That's my last slide here. But I just want to leave you with a little bit of a sense of awe there.